In order to discuss the behavior of conductors in electric field, we need to study the distribution of electric charge, the electric field and the potential in them. Let us suppose that a charged metallic conductor is in equilibrium state, that is, its electric charges are at rest from phenomenological point of view. Then the previously presented laws of electrostatic related to electric field strength, potential and charge can be applied in simple examples and thought experiments where we can draw the following conclusions. The first conclusion tells us that in the case of equilibrium, the electric field strength E is equal to 0 and the electric potential phi is constant inside a conductor. We can prove this statement by supposing that some excess charge distributed over the surface of the conductor produces a non-zero electric field inside the conductor. Then the electric field will act on the charge carriers, that is the electrons inside the conductor, and accelerates them in a given direction. The current due to the motion of charge carriers results in a spatial redistribution of them, reducing the electric field till it vanishes completely. The redistribution of charge or the establishment of electrostatic balance is an extremely short process. For the vanishing electric field strength E inside the conductor, the negative gradient of the electric potential phi is equal to 0, that is, the potential phi must be constant inside the conductor. The second conclusion states that in the case of equilibrium, the electric field strength E must be perpendicular to the outer surface of the conductor. For if the vector E was not perpendicular to the surface, then it would have not only a normal component but a tangential component accelerating the charge carriers on the surface. As a result, the charge carriers would be displaced over the surface by the electric field, producing a current over the surface. Since there is no current in equilibrium, the vector E must be perpendicular to the surface of the conductor with a vanishing tangential component, that is, the surface of the conductor is an equipotential surface. But we have already seen that the electric potential inside the conductor is constant, and the whole conductor is then an equipotential domain. We also have a third conclusion stating that in equilibrium an excess electric charge is distributed over the outer surface of a conductor. This conclusion follows from another thought experiment. Let us consider a closed Gaussian surface S inside a conductor close to its outer surface. Since there is no electric field inside the conductor in electrostatic equilibrium, the flux phi sub E of the electric field strength E passing through the Gaussian surface S vanishes. Then it immediately follows from Gauss' law that the total charge enclosed by the surface S is equal to 0. This statement holds for any closed surface of arbitrary size and shape inside the conductor. As a result, in the electrostatic equilibrium there is no excess charge inside the conductor, and the charge is distributed over its surface, and this distribution is described by a given surface charge density sigma. These conclusions drawn from the thought experiments can be demonstrated by the following experiment. First, we give some amount of electric charge to a metal box with a hole on it which is electrically insulated from its environment. If we bring an electrically neutral metal sphere into contact with the outer surface of the metal box and touch the plate of a discharged electroscope with the metal sphere, then the electroscope will show that the metal sphere attained charge. However, if we bring the electrically neutral metal sphere into contact with the inner surface of the metal box, then the electroscope will indicate that the metal sphere remained neutral, that is, it did not attain any charge. In the second experiment, we give some electric charge to the metal sphere and bring it into contact with the outer surface of the electrically neutral metal box. Then we touch the plate of the electroscope with the metal sphere and the electroscope will show that the sphere remained charged. However, if we bring the charged metal sphere into contact with the inner surface of the electrically neutral metal box, then the electroscope will indicate that the metal sphere became neutral, that is, it lost all the charge. The result of the experiment shows that when the metal sphere is brought into contact with the outer surface of the metal box, then the sphere will either attain or keep some amount of charge, since the sphere and the outer surface of the box forms one system and the sphere is the part of the outer surface of the system. When the metal sphere is brought into contact with the inner surface of the metal box, the sphere either loses all its electric charge, which will move to the outer surface, or does not attain electric charge at all, since the sphere and the inner surface of the box form one system. If we examine the electric field inside a cavity of a charged conductor, then we will find the following. In equilibrium, the electric field vanishes inside a cavity of a charged conductor and no electric charge can be distributed over the surface of the cavity. We can prove this statement by considering a Gaussian surface S inside the conductor where the surface encloses the cavity. We have already seen that there is no electric field in a charged conductor in equilibrium, and any excess charge is always distributed over its outer surface. Since the electric field strength E is equal to 0 at any point of the surface S, Gauss' law tells us that the total electric charge Q must be 0 within the volume enclosed by the surface S. The condition of vanishing net charge within this volume only demands that either there is no electric charge within the volume at all, or the volume contains an equal amount of positive and negative charges. In order to see whether positive and negative charges can exist over the surface of the cavity of the charged conductor in equilibrium, let us suppose that some positive charge is distributed over a part of the surface of the cavity. Then there must be the same amount of negative charge distributed over another part of the surface of the cavity, giving zero net charge within the volume enclosed by the surface S. The charge distributed over the surface of the cavity produces an electric field E in the cavity. The electric field lines must start at the positive charges and terminate at the negative ones because there are no free charges in the cavity. Let us consider a closed curve C inside the conductor intersecting the cavity. We can calculate the line integral of the electric field E along the section of the curve C between the positive and negative charges in the cavity, which is non-zero. When we perform the integration along the part of the curve C in the conductor where the electric field vanishes, we obtain zero. The line integral of the electric field E along the closed curve C given by the sum of the two integrals does not vanish, that is, the curl of the field E is non-zero. However, this result contradicts the fact that the curl of an electrostatic field vanishes, that is, its cyclic integral is equal to zero, which forbids the presence on electric charges distributed over surface of the cavity, proving the statement. We note that a cavity in a charged conductor can still contain electric charges in equilibrium, provided some charge distributed over an insulator or a charged conducting material insulated from the conductor is placed into the cavity. Now we will study the electric field due to the electric charge distributed over the surface of a conductor. We have already determined the electric potential of a field produced by a given distribution of electric charge over a surface in general case. Let us start with a simple example, where we calculate the electric potential produced by a uniformly charged conducting spherical shell S of radius R at a point P at the distance r from the center O of the sphere. Since the distribution of the electric charge over the surface of the spherical shell is uniform, the surface charge density sigma is constant and equal to the total charge Q of the shell divided by the surface area of the sphere, that is 2 pi times R squared. For a given surface charge density sigma, we found that the electric potential phi at the point P is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the surface integral of sigma divided by the distance r prime of the area element ds at the point P prime from the point P, over the charged surface S. In order to determine the area element ds in the integral of the potential phi, we consider a spherical annulus or ring generated by rotating the arc of the length R times d theta about the axis passing through the points O and P. Here d theta is an infinitesimal angle measured in the vertical plane passing through the axis of rotation. Then the area of the spherical annulus of infinitesimal width can be chosen as the area element ds, which can be written as the width R times d theta, times the circumference 2 pi times R times the sine of the angle theta between the line sections OP and OP prime. This gives 2 pi times R squared, times sine theta times d theta. If we substitute the expressions obtained for the surface charge density sigma, the area element ds, and the distance r prime between any point P prime of the area element and the point P, we have 1 over 4 pi times epsilon naught, times the integral of Q divided by 4 pi times R squared, times 2 pi times R squared times sine theta divided by the distance r prime. We can determine the distance r prime between any point P prime of the annulus and the point P by applying the law of cosines for the triangle OP prime P, which tells us that r prime is equal to the square root of r squared plus R squared, minus 2 times r times R times cosine theta. Then the potential can be written as Q over 4 pi times epsilon naught, times the integral of sine theta over 2 times the square root of r squared plus R squared, minus 2 times r times R times cosine theta, with respect to theta from 0 to pi. If we introduce the variable x defined by r squared plus R squared, minus 2 times r time R times cosine theta, then we can write the differential of x as 2 pi times r times R times sine theta, times d theta. By substituting this variable into the integral, we obtain Q over 4 pi times epsilon naught, times 1 over 4 times r times R, times the integral of 1 over the square root of x with respect to x. The lower and upper limits of the integral are x evaluated at theta equals to 0 and pi, respectively. Now we compute the definite integral, which gives 2 times the square root of x, and we can write the potential as Q over 4 pi times epsilon naught, times 1 over 2 times r times R, times the square root of r squared plus R squared, minus 2 times r times R times cosine theta, evaluated at theta equals to 0 and pi. If we substitute the lower and upper limits into the equation, then the expression in the brackets leads to the square root of r squared plus R squared plus 2 times r times R, minus the square root of R squared plus capital R squared minus 2 times R times capital R. As a result, the electric potential phi at the point P at the distance from the center O of the uniformly charged spherical shell of radius capital R and total charge Q, can be written as the total charge Q over 4 pi times epsilon naught, times the difference between the magnitude of the distance R plus the radius capital R and the magnitude of R minus capital R, over 2 times R times capital R. We can expand this expression and write the potential as 1 over 4 pi times epsilon naught, times the total charge Q divided by the distance R, if the distance R is greater than or equal to the radius capital R, and 1 over 4 pi times epsilon naught, times the total charge Q divided by the radius capital R, if the distance R is less than the radius capital R. The plot of the electric potential as a function of the distance R shows that phi is constant within the uniformly charged spherical shell, and it is inversely proportional to the distance outside the spherical shell. Now we derive the electric field strength from the potential obtained here. The electric potential due to a uniformly charged spherical conducting shell is constant inside the shell and inversely proportional to the distance outside the shell, which is a spherically symmetric function about the center of the shell. Then we can use a spherical coordinate system with its origin at the center of the spherical shell to describe the electric field strength E given by the negative gradient of the electric potential phi. If we write the gradient of the scalar function phi in spherical coordinates, then we immediately see that the polar and azimuthal components of the gradient vector vanish due to the radial symmetry of the potential. The electric field strength E at a given point has the magnitude of 1 over 4 pi times epsilon naught, times the total charge Q of the shell divided by the square of the distance R between the origin and the point, and points in the radial direction. Here the basis vector E sub describing the radial direction R is simply equal to the position vector R pointing from the origin to the given point, divided by its length. As a result, we regain the expression derived when we computed the electric field strength for a spherical shell of a uniform surface charge by applying Gauss' law. If we inspect this result with the electric potential and the magnitude of the electric field strength plotted as a function of the distance from the center of the shell, we can conclude the following. The electric field produced by a uniformly charged conducting spherical shell of total charge Q outside the shell is the same as the electric field produced by a point charge Q located at the center of the shell, and vanishes inside the shell where the potential is equal to the potential on the surface of the shell. We note that when we determine the electric field due to a uniformly charged sphere of total charge Q, we saw that the field outside the sphere is also the same as the field produced by a point charge Q located at the center of the sphere. Essentially, we can replace both the uniformly charged conducting spherical shell and the uniformly charged sphere by a point charge of the same charge, when we study the electric field outside the shell or the sphere. In fact, this statement can be generalized for any spherically symmetric distribution of charge within a finite volume by applying Gauss' law for a spherical Gaussian surface enclosing the given volume with the center at the center of the spherical symmetry. We have studied the electric field due to a uniform surface charge distribution in a conductor. In the most general case, the distribution of electric charge over the surface of a conductor is not uniform, that is, the surface charge density sigma defined by the derivative of the charge Q with respect to the surface area S can change over the surface. We can experimentally verify that the surface charge density and the electric field strength is greater where the surface of a charged conductor is more curved. If we bring electric charge on the conductor made of a metal cylinder and a metal cone on its top as seen in the figure, then a non-uniform electric field is produced by the charge over the surface of the conductor. We can determine the strength of the electric field at different points of the surface, let us say at the points A, B and C where the surface has different curvature. If we bring an electrically neutral metal sphere into contact with the conductor at the point A, and then touch the plate of an electroscope with the sphere, the device will indicate that the sphere attains some charge. If we recharge the conductor so that it has the original amount of charge and discharge the metal sphere, then we can touch the conductor at the point B with the electrically neutralized sphere, and test the amount of attained charge with the uncharged electroscope. We can recharge the conductor and discharge the metal sphere again, and we repeat the experiment by bringing the metal sphere into contact with the conductor at the point C. Then the metal sphere will attain a given amount of charge, as indicated by the electroscope. A comparison of the results of the three cases shows that the amount of charge attained by the metal sphere is the smallest in the first case because the point A is on the flat bottom of the conducting cylinder. More charge is brought from the point B to the sphere in the second case, where the point B is on the curved surface of the cylinder. The greatest amount of charge is attained by the sphere in the third case, since the point C is at the top of the conducting cone. In the next step we will determine the explicit relation between the electric field due to the charged conductor and the surface charge density on the conductor. Let us consider a small cylinder intersecting the surface of a charged conductor as seen in the figure. Since the electric field strength E vanishes within the conductor, it gives a contribution to the electric flux passing through the cylinder only outside the surface of the conductor. If the cylinder is small enough, then the electric field lines emanating from the surface of the conductor in the normal direction remain parallel with the curved surface of the cylinder and they pass through only its top. By considering this cylinder as a Gaussian surface, we can apply Gauss' law stating that the surface integral of the electric field strength E over the cylinder is equal to the total charge Q enclosed by the cylinder over epsilon naught. On the one hand, if S is the surface area of the top of the small cylinder, then the surface integral is equal to the magnitude of the electric field strength E perpendicular to the top, times the surface area S. On the other hand, the total charge Q is given by the surface charge density sigma over the surface of the conductor times the area of the intersection of the surface of the conductor and the cylinder, which is also equal to S. Then the magnitude of the electric field E produced by the electric charge distributed over the surface of a conductor is equal to the ratio of the surface charge density sigma to the vacuum permittivity epsilon naught. If we compare this result with the one obtained for the electric field due to a uniformly charged infinite plane, we can see that the magnitude of electric field strength is 2 times less for the infinite plane than the one for the charged conductor. The explanation of this fact is simple. The charges in the vicinity of a given point of the surface of a charged conductor produce a local electric field in both sides of the surface, which is given by the surface charge density sigma around that point over 2 times epsilon naught. However, the rest of the charges distributed over the whole surface also gives a local contribution to the electric field, which is equal to the same surface charge density sigma over 2 times epsilon naught. As a result, the total electric field at the given point is equal to 2 times the local field, that is sigma over epsilon naught outside the conductor, and vanishes within the conductor. We can demonstrate the inverse proportionality between the electric field strength and the curvature radius of the surface of a charged conductor with the following simple example. Let us consider 2 small conducting spheres of radii R1 and R2 connected by a long conducting wire. If we bring electric charges into this system, then both the spheres will attain some charge. Since the surfaces of conducting spheres in contact represent an equipotential surface, we can write the electric potential phi over the surface of the first sphere as 1 over 4 pi times epsilon naught, times the total charge Q1 attained by the sphere divided by its radius R1, which is equal to the electric potential phi over the surface of the second sphere, that is 1 over 4 pi times epsilon naught, times the total charge Q sub 2 attained by the sphere divided by its radius R sub 2. It follows from this equation that the ratio of Q sub 1 to R sub 1 is equal to the ratio of Q sub 2 to R sub 2, or Q sub 1 over Q sub 2 is equal to R sub 1 over R sub 2. This relation tells us that the amount of electric charge attained by each conducting sphere is proportional to the radius of the sphere. Then we immediately see that the surface charge density over each conducting sphere given by the ratio of the total amount of charge attained by the sphere to the surface of the sphere, is inversely proportional to the radius of the sphere. That is, the ratio of the surface charge density sigma sub 1 over the first sphere to the surface charge density sigma sub 2 over the second sphere, is equal to the ratio of Q sub 1 divided by 4 pi times R sub 1 squared to the ratio of Q sub 2 divided by 4 pi times R sub 2 squared. By substituting the expression obtained for the ratio of the total charges into this equation gives R sub 2 over R sub 1. Since the magnitude of the electric field strength produced by a charged conducting surface is equal to the surface charge density over the surface divided by epsilon naught, we conclude that the magnitude of the electric field strength E sub 1 for the first sphere divided by the magnitude of the electric field strength E sub 2 for the second sphere, is equal to the ratio of the radius R sub 2 of the second sphere to the radius R sub 1 of the first sphere. In other words, the electric field strength is inversely proportional to the radius and the field strength is greater over the parts of conductors having more curved surface or smaller curvature radius. We note that the distribution of the electric charge over the surfaces of the spheres is not strictly symmetric because the charge on one sphere changes the distribution of charge over the other sphere and vice versa. In this figure we show the electric field produced by a charged conductor with flat faces and sharp edges where the continuous lines mean the electric field lines, and the equipotential surfaces or lines are represented by dashed lines. The field lines emanating from the edges indicate a very strong electric field at the edges. We can also see that the profiles of the equipotential surfaces closer to the surface of the conductor are more like the profile of the surface of the conductor, which is itself an equipotential surface. This example shows that the electric field close to the tip of a sharp conductor can be strong enough either to ionize or polarize the gas molecules of the air in the vicinity of the tip. When it occurs, the ions of charge opposite to the charge on the conductor or electric dipoles are attracted to the charged tip and neutralized on it, reducing its charge or attaining a tiny part of the charge on the conductor. However, ions with like charge are accelerated in the opposite direction by the strong electric field, that is, the charge accumulated at the pointed end of the conductor will repel them. These ions drag the neutral gas molecules along and together produce a detectable motion, that is, an air flow around the tip of the charged conductor, known as electric wind. As a result, the conductor loses charge since charges emanate from the tip and exit with the electric wind. This phenomenon is called electric point effect. In order to demonstrate the electric point effect, we present the following experiments. If we attach a tip to the top of the cone of the metal container used in one of the previous experiments and the whole conductor is continuously charged through a conducting wire, then the flame of a candle placed in the front of the tip is pushed away from the tip by the electric wind. If the effect, that is the air flow bending the flame, is strong enough, then it can even extinguish the candle. Since the charge exiting from the conductor through the wind is compensated by recharging the metal container through the wire, the electric point effect can be maintained and the electric wind will continuously blow in the direction of the candle. In another experiment, the action-reaction force pair is applied on a continuously charged fan, where the action is the repulsive force exerted by the tips of the four metal blades of the fan due to the electric point effect, and the reaction of the action keeps the fan spinning. In the next experiment we can demonstrate that the charged conductor A with a tip will lose a given amount of charge, whereas an electrically neutral conductor B placed in the front of the tip will attain like charges in the electric wind originating from the tip. This effect is not a simple separation of charge because the conductor B will keep the attained charge even if the conductor A is removed from its vicinity. We can invert the direction of the process by charging the conductor B and place the electrically neutral conductor A with its tip close to the charged conductor B. The charge on the conductor B causes a separation of charge on the conductor A, and its tip will obtain opposite charges. A given amount of this opposite charge will exit from the conductor through the electric wind while like charges remain there, and as a result, the conductor A attain like charges. It follows from these findings that if we want to prevent charge from leaving a charged conductor through an electric wind or discharge, then the surface of the conductor need to be smooth enough so that we can avoid the occurrence of the electric point effect. However, this effect can also be important in practical applications of very strong electric fields, as we will see in the next examples. The first example is the field emission microscope. The photo shows the tube of a field emission microscope, and a schematic diagram of the device can be seen in the left-hand side. Its operation is based on the effect of the very strong electric field produced close to the extremely sharp tip of a metal pin. The pin is placed in an evacuated space enclosed by the tube, and its very fine tip with a curvature radius of about 10 to -7 meter is used as a cathode. The strong electric field with the field strength between 10 to 9 and 10 to 10 volt per meter draws electrons from the tip of the cathode held at a large electric potential. The electrons emitting from the cathode are accelerated in the direction perpendicular to the surface of the pin by the huge potential difference between the pin and the fluorescent layer on the inner surface of the tube. The electrons traveling along the field lines collide with the tube and produce a bright pattern on the fluorescent screen, as seen in the figure. These patterns represent a magnified image of the crystal structure of the pin or the molecular structure of any material sample covering the tip of the pin. The magnification is proportional to the ratio of the curvature radius of the fluorescent screen on which the image is formed to the radius of the tip. For field emission microscopes, the magnification may reach up 1 million times the scale of the sample, but we can achieve even 10 times more magnification with field ion microscopes. Field ion microscopes work with low-pressure helium gas instead of vacuum, and the polarity of their pin is reversed, that is, the pin is used as an anode. The helium atoms colliding with the tip of the pin become ionized by losing one electron, and the positively charged ions traveling from the tip to the bulb will produce the magnified image on the screen with a much higher resolution than the one obtained with field emission microscopes. The next example for applications utilizing the electric point effect is an electrostatic machine producing high statics voltages, that was designed by Robert J. van de Graaff, an American physicist, and it is known as Van de Graaff generator. A specimen of this apparatus is seen in the photo, and this schematic diagram will help us to understand its working principle. A rubber belt, sometimes made of silk or other elastic dielectric material, runs between two rollers driven by an electric motor. Due to the point effect, the belt attains charge from the tip held at the potential of couple thousand volts, and the charge is transferred by the moving belt into a hollow metal sphere, also known as dome. The original design of the generator uses triboelectric effect between the roller and the belt to separate charges, which causes a strong buildup of charge on the roller and opposite charge on the belt. Instead of a charged pin, the pins of a grounded comb close to the lower roller and the belt producing electronic point effect transfers more charge from the grounded comb to the belt. Inside the dome, another tip or a comb with many tips attached to the metal sphere gathers the charge from the belt due to the point effect, and the assembled charge will spread out across the whole spherical shell. Since the belt continuously carries charge from the voltage source to the dome, such an amount of charge can be accumulated on the spherical shell, which is only limited by the insulation of the device, the size of the dome and the distance of the dome from other objects. The upper limit of the statics voltage produced by a Van de Graaff generator may reach up to several million volts, and the device was used to accelerate particles up to reasonable high energies in nuclear physics. The last example for the application of the electric point effect is another electrostatic generator or influence machine invented by James Wimshurst, a British electrical engineer. The photo in the schematic figure illustrates its operation. The apparatus consists of two counter-rotating insulated discs which are covered with tinfoil sectors spaced at regular intervals. The rotating discs pass two pairs of metal neutralizer bars and their brushes set at right angles to each other, where the brushes are positioned near the surfaces of each discs. The brushes are denoted by the letter B in the figure. If a small amount of charge already resides on any of the sectors, then a process can start where each sector induces an equal and opposite charge on a passing sector on the other disc. The charges are collected by the two pairs of neutralizer bars and their brushes, applying the electric point effect, and allowing an exponential accumulation and separation of positive from negative charge at the output terminals T connected to the bars. At maximum output of the influence machine, the voltage at the terminals can range up to 10 to 4 volts, but the charge accumulated per second only reaches 10 to -5 coulombs. Then the current produced by the apparatus is usually 10 microamperes or less, and a Wimshurst machine is not suitable for being a current source. In the previous examples we examined how charged conductors can produce electric field, but in some cases we also studied the behavior of electrically neutral conductors in the vicinity of charged ones. If an electrically neutral conductor is placed in an electric field, then the positive charge carriers in the conductor are accelerated by the electric field strength and gain velocity in the direction of the field, whereas the negative charge carriers are pushed in the direction opposite to the field. The two ends of the conductor therefore attain opposite charges, producing an electric field inside the conductor, where the external and the internal electric fields have opposite directions. The displacement and the redistribution of the charge carriers will not stop until the electric field inside the conductor drops to zero and the electric field lines become perpendicular to the surface of the conductor. As a result, the electric field strength of the induced charges at the boundary surface of the conductor and the electric field strength producing the separation of charges cancel each other out inside the conductor. Outside the conductor, the field produced by the induced charges has a positive contribution to the external field at the two ends of the conductor, increasing the field strength there, whereas it has a negative contribution at the two sides of the conductor, decreasing the field strength there. These findings show us that the metal sphere used to measure the electric field strength in the previous experiments needs to be small enough and attain so small amount of charge that it has no significant effect on the electric field, and produces only a negligible modification in its field strength. For a conductor with a cavity, the induced charges have a distribution over the surface of the conductor in equilibrium such that the electric field vanishes within the cavity. In other words, the external electric field cannot penetrate the cavity because the conductor shields the cavity from the electric field. A metallic enclosure, for example a fine metal mesh known as Faraday cage, can provide a perfect electrostatic shield for the space enclosed by it. If a discharged electroscope is placed in a Faraday cage and a charged body producing a strong electric field is brought close to the cage, then the electroscope will not indicate any presence of the electric field. However, outside the cage, the foil leaves of the electroscope will move apart due to the separation of charge produced by the charged body. The electrostatic shielding effect of a metal box or a fine metal mesh is very useful for protecting sensitive devices from electromagnetic interference or any object from lightning strikes.